Hi, we continue Wilcoxon signed rank test. So last time that we explored the concepts of the signed rank test. So this time that we do this in our language. Okay, so remember that we have the summation of positive ranks and summation of the negative ranks. And summation of positive ranks is denoted as V, and V asterisk is 19. So remember that we have 7 observations. So summation of V and V asterisk is always 28. And if the V is too small or too large, that we may reject the null hypothesis that mu is equal to 79,500. And that test can be done by this Wilcox.test function. So Wilcoxon signed rank test. So we get V automatically. So income includes the 7 income of math PhDs, and we get p-value is equal to 0.4688. So that means the distribution of V, so distribution of V is, okay, so discrete, but it takes time to write down. So just conceptually, we write the some curve. Okay, so then V is equal to 9 is here. Maybe I explain this. Okay, so this is V is equal to 9. And corresponding one is 19. And the smallest possible value is 0. Largest possible value is 28. Then p-value is 0.4688 for two-sided test. That means the area of this part plus this part is equal to 0.4688. So that means that this area is equal to half of that number. So this is 0.4688 over 2. So about 0.2344. And so this. So in this case, that we don't reject null hypothesis because p-value is larger than alpha. So suppose the alpha is 0.05, then we have a larger p-value than this. So we do not reject H naught. Yeah, and actually the p-value is larger than the t-test we have seen in earlier section, the 5.1. What was the p-value in the t-test? The p-value was actually equal to 0.38. So 0.38 was the p-value for t-test. So p-value is slightly larger. And it's consistent with the fact that the Wilcoxon signed rank test has lower power. So we have, I mean, it's more difficult to have smaller p-value for Wilcoxon signed rank test. Okay, so next, the one-sided test. We want to test if mu is smaller than 79,500. So that means that this is alternative, and the null hypothesis is mu is equal to 79,500, and we excluded the possibility that mu is larger than 79,500. So we strongly believe that math PhD earn less than or equal to other PhDs. So that is the assumption of this test. So Wilcoxon.test. So this time that we have the same code. So X is the income. So actually we have slightly different code, but anyway. So this is income, and alternative is equal to less. If we specify this option, that we can do one-sided test. And actually there's almost the same result. V is equal to 9. This does not change. This is based on the null hypothesis. Oh, sorry. This is based on the data, and it doesn't be changed by the alternative hypothesis. And the p-value is 0.2344 because we only have the one-sided p-value. So V is here, and the distribution of V is here, and 9 is here. Then p-value is just one side, so that this side only. So this is equal to 0.2344 as seen in the previous slide. So still H0 is not rejected. So one-sided test, it's easier to reject because we have strong assumption that X mu is never larger than 79,500, but still that we cannot reject in this case. And another one-sided test. How about the H1 is mu is larger than 79,500? Then we can specify alternative is equal to greater. Then we can do the same test. So V is equal to 9, then p-value is 0.8125. So basically that we calculated the area of the other side. So distribution of V is here and here, and V is equal to 9 is around here. And last time that we calculate the area below 9, but this time the above 9. So this area, this entire area. So this is equal to 0.8125 as indicated here. So last time the 0.2344. So actually this and this, almost the sum up to 1, but actually slightly more than 1. Why? Because we have duplication. V is equal to 9 is duplicated. So this is just how to define the p-value. But the p-value, if p-value is small, we reject null hypothesis. So we want to only get that conclusion if there is a strong evidence. So we are a little bit conservative that the p-value is p-value includes this area. So it's slightly harder to reject null hypothesis in that case. Okay, so we don't do exercises in this video, but it's good to see these exercises to understand how to calculate the distribution of V. So exercise 1, do a simulation to calculate probability of V is less than 9 when the sample size is 7. So basically the distribution of V only depends on the sample size. So 7 is given, then we should be able to calculate sample size V, sample distribution of V. Okay, so how to do that? At first, generate the 7 random numbers from 0, and then calculate V. Then we repeat this 10,000 times. So for example, suppose x1 to x7 follows normal 0, 1. So that is symmetric around 0. So 0, 0, 1. So then, okay, so maybe the 7 random numbers are negative 0.4, the positive 0.6, the negative 0.1, positive 1.5, the positive 1.1, and negative 0.9, and a positive 0.3. Then what are the ranks of these observations? So if you ignore sign, this is rank 1, rank 2, rank 3, rank 4, rank 5, rank 6, and rank 7, and think about sign, the negative, negative, negative. So in this case, the V is equal to the sum of positive ranks. So 4 plus 7 plus 6 plus 2. So this is 19. And V asterisk is negative ranks. So the 3 plus 1 plus 5. So this is 9. So V, and we repeat this the 10,000 times. Then we have the empirical distribution of V. So we can simulate the probability of V is less than 9. And this distribution, normal 0, 1, does not really matter as long as it's symmetric around 0. So if we simulate the same thing by x1 to x7 follows, for example, uniform from negative 0.5 to 0.5, but still, okay, random numbers are different, but the distribution of V that remains the same. So this is the exercises to see how to calculate the distribution of V.